Okay, so we're starting on chapter 2. Oh, this February 21st. If you came in late, Rebecca Adams is coming to speak here. She's a former student. I think she's a grad student at Tulane, but she's coming to talk about her work there. She's a chemistry uh, researcher. So I'll send you more details over email about this. We're moving into chapter 2. In chapter 2, we're going to see potential. It's kind of a difficult topic, but I think y'all will be okay. It's difficult just in the sense that it's kind of abstract. And then also in chapter 2, which will also be on this next exam, I don't know, in 2 or 3 weeks, will be capacitance. And we're going to get into circuits. And then we'll be in circuits the rest of the year, I think. Like, we'll be in circuits, yeah, for the rest of the time. And so I think y'all like circuits. It's a lot different than what we've been doing. It's more less abstract than what we've been doing. So I think you'll really like circuits quite a bit. All right, so let's just define what is potential difference and electric potential. Remember, so far we've been dealing with forces, fields, and now we're going to add in potential. Now fields, if you remember, were a force per unit charge. Now we're going to add in potential, and potential is an energy per unit charge, and then later we'll deal with potential energy, which of course is just energy. So we're going to have these, we're going to sort of add these to our quiver of how we describe electricity and electrical charges. Electric forces, as you know, are conservative, just like gravitational forces. What do those two forces have in common? Electric and gravitational forces, they're what types of forces? They are conservative, yeah, but another word that all conservative forces are field forces, right? So these are field forces. Gravitational and electric forces are field forces. That means that they don't require contact between two objects. Anytime you have contact between two objects, those forces are non-conservative. They lose a little bit of energy. We talked about this last semester, how friction, for example, is a non-conservative force. It loses energy when it acts. So conservative means not political or religious or any of that business, but when we talk about conservative, it means that we conserve energy. The force conserves energy. And generally in science, when we say something is conservative, that's what we mean, that it conserves energy. And a conservative force is path independent. Remember we talked about last semester, like we had a mountain and we go up a couple different ways. Like if we go up this way, we gain a certain amount of energy. We have a change in potential energy. And then also if we go up this way, we gain the same amount of potential energy, that those two are equal. That means that a conservative force, it doesn't depend upon the path that you take, that you're still going to have the same change in energy. Whereas a non-conservative force, if I take the red path or the blue path, the non-conservative force that will lose the most energy is the which path? The red path, right? Because you travel a much longer distance, so that force has a longer distance over which to act, so it does more work, or it takes away more energy. All right, so conservative is a force that conserves energy. The amount of work done by the force changes the energy by the same amount. So the work changes the energy by the same amount. That is, that work is equal to our change in energy. There's no lost energy. And a non-conservative force doesn't conserve energy. And in this case, the work done is generally greater than the change in energy because you're losing energy. The work done by conservative forces is path independent. The work done by non-conservative forces is path dependent. We had all this last semester. In fact, I think I just copied this from last semester. But just to jog our memory on what these terms mean. All right, so for conservative forces, work is equal to our change in kinetic energy. Now, if work causes an increase in kinetic energy, then what happens to the potential energy? Like if I have a set amount of energy in a system, and if I cause the kinetic energy to go up, what would I say happens to the potential energy if I have this set amount? It's going to go down. So we'll use this idea that the change in potential energy is equal to the negative of the work as an object moves from one position to another. The negative isn't really that big of a deal when we get into the nuts and bolts of things, but you'll see this negative, and I just want you to know that that's sort of where it comes from. That when I have a change in potential energy, that's due to a negative, that's seen as like a negative of the work. And this will always apply when the electric field is constant. We'll get into some areas when the electric field is not constant over space. We'll always deal with time constant electric fields, but we'll see what happens when our electric field varies through space later, and we'll do some cool partial derivatives that you've probably never seen before, but they're really just derivatives. Don't freak out. It'll be okay. All right. So let's imagine that I have this electric field. This is like what y'all set up in lab at the very beginning, where I have a charge plate on this side, a charge plate on this side. They're positive and negative. So I have positive charges over here. I have negative charges over here. If you remember in the lab, the field lines actually curved around on the outside, but we won't worry about that. I just want to think about the field lines as they go across the plates, as they move from one side to the other. These are constant electric fields. They don't change in time. They don't change in space either. They're always the same value. And I know they have the same magnitude, by the way, because the electric field lines, what gives the magnitude of the electric field? Right, the density of the line. So here the lines are equally spaced at all points, so I have a constant electric field. All right, so I'm going to think about a particle that moves from point A to point B. And then also one other thing, I'm going to go ahead and throw out these terms. That I'm going to call this the high potential side. I'm going to call this the low potential side. That'll help you sort of cement those terms in your mind, because it'll come up again later. High potential is the positive side. And you can think about a positive charge here, that if I put it here, it has a high potential for motion. It has a lot of energy per charge. And this positive charge is always going to move towards the low potential. You can see that because it's repelled from this side, it's attracted from this side. All right, so has the electric field, remember the electric field is a field of forces, has it done positive or negative work on this positive charge as it moves from this position to this position? Which is it? Remember, work is F dot D. Has it done positive or negative work as it moves from A to B? It's done positive work, right? There are two things that we're concerned about. The direction of the force, which is to the right, the direction of the displacement, which is also to the right. So our dot product then is positive. Work equals F dot D. F and D are both in the same direction, so this is equal to plus FD, well, it's actually FD cosine of 0 degrees, and the cosine of 0 is 1, so this is plus FD, because they're in the same direction. Now, the work is positive, so has the potential energy of the positive charge increased or decreased? It's decreased. Remember, our work is equal to the negative of the change in potential energy, so the potential energy has decreased. And so where has the energy gone? If my potential energy is decreased, but I've done work on this object, what kind of energy does it now have? It has kinetic energy. And so this is a really great thing about work and energy, is that we can use our electric field and the distance over which it travels to figure out what is the kinetic energy of this object. So whatever the work that is done is equal to a change in kinetic energy. So if the charge has lost potential energy at point B, its kinetic energy is increased. Then we can calculate the charge's speed, because the kinetic energy is 1/2 mv squared. So the work done by the electric field is equal to our change in kinetic energy. All right, let's see, I think I have an example next. We've done some problems like this before, right? Something similar or no? I don't remember. We sort of been dealing with things similar, but we might not have done this exactly. All right, so let's say I have a proton released at x equal -2 centimeters in this electric field, and I just want to know its velocity. So I say that the work done by the electric field is equal to the change in kinetic energy. The work done by the electric field is the force times the displacement, and that's equal to 1/2 mv squared. That's what is the force? The force is equal to Q times E, right? F is equal to QE. And by the way, on the test, we had a problem where you had to figure out the force. Well, first you had to figure out the net electric field, and then you had to figure out the force. And a good portion of you used Coulomb's law to figure out the force. And then you sort of had some of you had errors along the way. It was the much easier way is once you know the electric field, you can find the force on the charge just by multiplying that electric field by the charge. So that second part was supposed to be simple, but some of you made it more complicated than it needed to be. It's okay. But anyway, our force is Q times E times our distance, which is our delta x. And that's 1/2 of the mass times v squared. So we can solve for v here. And it's going to be what? 2 Q E delta x divided by m and square root of all that jazz. And that gives us our speed. Taking Q for a proton is 1.6 coulombs, and mass of a proton is what, 1.67. If you don't know these values, I expect many of you know them by now, but if you don't, they're on the equation sheet up in the upper left-hand corner. And our electric field is given. Our delta x is 10 centimeters, or 0.10 meters. And then that'll give us our speed, 1.4 times 10 to the 5th meters per second. On the test, you had to use Newton's second law to figure out the acceleration, and then you weren't looking for the speed, but you were looking for the displacement. But if you're looking for the speed, you can use this energy argument. It's a lot easier to do so. And especially you chemists, as you work with charged particles and ions and all that business, and some instruments, like the mass spectrometer, for example, you use electric fields to accelerate those particles to particular speeds. We'll talk about the mass spectrometer in chapter 5 or 6 a little bit later, but because it includes magnetic fields as well. But electric fields are handy for this to accelerate particles to a certain speed.
10 meters.
Okay, good question. So I'm going from -2 to 8 centimeters. So my change in position is 8 minus -2, which is 10. So that's 10 centimeters. But 10 centimeters, changing it to SI units is 0.1 meters. Is that clear? Okay. Thank you. Sorry for that. Okay, so talking about potential now, we're often going to talk about electric potential difference. And we'll sort of use these terms interchangeably. Potential, which will be the energy per charge at a particular point in space. We'll also talk about potential difference, which I'll call delta V. This is going to be the difference in the energy per charge between 2 points in space. And then later when we get into circuits, we'll just scrap all that and we'll just call it voltage. All right, like the voltage of our outlet is 120 or 110 volts. But we'll sort of use those interchangeably, though there are slight nuanced differences in them. The potential is the energy per charge, is the energy per charge at a particular point in space. The potential difference is the energy per charge between 2 points in space. What's the difference in energy between these 2 points? We've sort of seen that already, like with gravitational potential energy. What's the difference in the gravitational potential energy between these 2 points? Sort of something like that. And then voltage, we'll sort of keep that for circuits, but that's sort of like a potential difference for circuits. Like what is the voltage across a battery or across a power supply? What's the difference in the energy per charge for that power supply? Okay? Sometimes students get those terms mixed up in their heads. They sort of are very similar, but they have nuanced meanings. So the electric potential difference between 2 points is the energy per charge gained as the charge moves from point A to point B. So we'll call this, the difference in VB and VA. So if I have 2 points, say point A and point B, and I have a charge that's, all right, I'm moving from one point to another, it's just the difference in the potential here and subtracted from here. We'll get more into what potential means later, but VB, or this delta V, is just the difference in the potential. The units, it's energy per charge, so that's 1 joule per coulomb, and we use, for voltage, we use the volt. So that's equivalent to 1 volt, or we'll capitalize it as capital V, because it's named after a person, Voltaire. All right? Wouldn't it be something if you guys had a unit named after you? Have you ever thought about that? Like a Roger or a Satterfield? Wouldn't that be cool? Yeah, Satterfield is kind of a mouthful, isn't it? What is that? Yeah, it's better than the smooth. But I don't think there are many units left to name, but maybe, some exotic particle you'll discover or whatever, or some exotic measurement that you'll do. They can name a unit after you. Okay. So since delta PE, the change in potential energy is negative of the force, that's QE, times the distance, that's delta X. Now, that's nothing new. We're just saying that the change in potential energy is the negative of the work. This is force times distance, QEX. That's on your equation sheet. Then delta VE is equal to delta PE over Q. That's our basic definition of what is voltage. Voltage is energy per charge. And so we can combine these two, and I get this is equal to negative E times delta X. And I'm going to say that E is in the X direction there. So it's in the same direction as the displacement. And so we get this expression that we'll see later, that EX is equal to negative of delta V over delta X. That's solving this equation here for EX. We'll see this again later. Like I said, we're going to get into some partial derivatives where we can take the voltage or the potential function and figure out what is the electric field. And you're going to really like it because voltage is a scalar quantity and electric field is a vector quantity. And so we'll be able to take that scalar quantity and figure out what is the electric field. You're going to love it because we love scalars, right? I like scalars. They're a lot easier to deal with than vectors. And so we'll be able to discard all that vector business that we did in the previous chapter and just deal with the scalar quantities. All right. So this gives us a more typical unit for electric field. I like to use newtons per coulomb because I always think of electric field as a force per charge. And when I think of newtons per coulomb, this is a force per charge. And that is, you know, at its basic level, what a field is. But often what people use for electric field is not a force per charge, but because E is equal to negative delta V over delta X, they'll use the unit of 1 volt per meter. And some of you that are going into health sciences, like pre-med or whatever, you'll talk about the cell, and you'll talk about the voltage between two walls of the cell, and sometimes you'll talk also about the electric field, because there's an immense electric field that runs between the cell membrane that causes those charged particles to move across the cell membrane. It's a very large electric field. The voltage isn't that big, but because the separation between across the cell membrane is so small, it gives us a very large electric field. You know what I'm talking about? You talk about nervous system a little bit, how charges move through the neurons. Yeah, maybe. You probably will when you take anatomy. You'll do nervous system and anatomy. Okay. All right. So now let's think about how charges move in a potential. Positive charges move from high to low potential. Or like I like to say, see if I can do this. They move from high to low, high to low. Can y'all do that? It's not that easy. Y'all try it real quick. You switch the tones, yeah. High to low. Just try it, for goodness sake. It's not that easy. You can't do it, can you? You try it later when you leave here. Because it took me a long time. It's like rubbing your belly and patting your head at the same time. Not easy to do. High. Low. Okay, negative charges, on the other hand, accelerate from low to high. See, I can't even, you got to think about high. And this is going to bring up an interesting thing that we can do with charges. We can move them around. We can create little potential wells where we can capture charges and make them stay in a particular place. Well, let's try these questions first, and then we'll talk about that. A positive particle is released at point A. This is a graph of potential versus position. All right, so it says, as I move through X, as X increases, the potential changes. In some cases, it's negative and approaching 0, and then it gets more negative and approaches 0, and then it gets bigger, and then it gets smaller. You can set these up pretty easily in the lab. You can build circuits to create certain potentials that act over a 1 or 2 or even a 3-dimensional space. And you can calculate what those potentials are. It's not that hard, actually. And so here, I represent the potential versus position, and if I release a positive particle at x equal a, I want to know, where's the particle going to go? Is it going to go to the left or right? Will it be stationary, or will it oscillate around B? What will this particle do? I have it at x equal a, right here, where the potential has this value. What's going to happen to that particle? All right, let's stop in about 5 seconds at 127. Okay, good. Positive particles move from high to low potential. I always like to think of positive particles, they act like particles of mass. If I have a positive particle here on the side of a mountain, this is high potential right here. This is low potential, low energy. It's going to move from high to low potential. So positive particles do sort of what a stone rolling down the hill would do. It would move from high to low potential. Maybe I've told y'all this one. Where does a one-legged, or what is the name of a one-legged lady? Eileen. I thought I told you that one. I told you that I have one, right? Yeah. So one day I'm gonna have a one-legged lady in this class. I'm not like half my jokes are just gonna be
What's her name really is Eileen?
inappropriate. Yeah, I've never had an Eileen, but I know several Eileen. All right. So if I let it go here, it's gonna move in this direction because it moves from high to low potential. What if it was a negative particle? What would happen? I do the same thing. I release it at x equal a. What's it gonna do? Huh. Yeah, you release it at x equal a, right here. What's going to happen to it? Hit the best. Okay, there's a lot of little muttering up here. Because there are actually two possible answers. And some of you pick one answer, and some of you pick the other answer. What are the two possible answers? Yeah, oh, B and D, right, yeah. So it can move to the right. And an electron does something different, or a negative particle. If I put a negative particle on the side of my mountain, it's not going to move down the hill, it's going to move up the hill. Like electrons do everything the opposite. It's like Bizarro World from Seinfeld. You know what I'm talking about? Y'all don't watch Seinfeld anymore, do you? Anyway, it's like Bizarro World. It's like everything's the opposite from what it was before. So an electron will not move from high to low, it moves from low to high potential. And so the negative particle will move from low up to high potential, but then it's going to sort of overshoot here and go to this side, and then it's going to say, oh no, I'm moving to low potential. And it's going to shoot back, and it's just going to oscillate around like that. And so let's put D for this one. D. I'm going to stop at D at 205. Sorry. And so a negative particle will move to the right, or it will oscillate around. So if I have, say, a positive particle right here, if this was a positive particle, it will also oscillate in this. We call this a well, a potential well. Let me get you out there. So what does a janitor yell when he jumps out of the closet? Surprise! You get it? Like surprise, but it's janitor. My mom was a janitor. She worked at a skating rink. And man, your parents ever work at a skating rink? It's like the best job in the world because you get to skate like all summer long and you get to make the cotton candy. And I was a DJ, for goodness sake. I was like 12 years old and they let me DJ up in the music thing. It was sweet. All right, so that's a potential well for positive particles. This would be a similar potential well for negative particles. Do y'all see the implications of this? You can take a particle and create a potential function in the lab in space, right, with circuits and with transducing plates. You can create this potential function that allows you to isolate charged particles and just hold them in space. You ever thought about that? Like, if you wanted to isolate a charged particle, how would you do that? You know, never crossed your mind? Like, it seems difficult when you start to think about it, right? You can't physically hold the thing in place. So how are you going to hold it? Well, this is how you can isolate these charged particles and hold them in space and then do whatever it is that you want to do with the charged particle. That's pretty cool, no? You create these potential wells that'll hold them in space forever, as long as you keep that well powered. All right, so this is important. It allows you to isolate, and hold charged particles. All right, let's see. Here are some. We did these simulations in the lab. Most or all of you are in the lab, I think. But if you want to practice with some of these, you can look at the different field configurations, and you can play electric field hockey if you forgot what the website. Here it is. Now let's look at potential and potential energy due to point charges. Remember, potential is energy per charge. It's kind of like the field. Remember we had the field, I had a charge in space. And then off to the side of the charge, we described the field. And it didn't really matter if there was another charge there or not. There was still a field there. And if I put a charge there, it would experience the force due to that field. But the field was created by the first charge. And so in a similar way, I'm going to have a charge, and then over here, whether there's a charge over there to experience it or not, there will be a potential. And where the field was a force per unit charge, the potential is going to be what per unit charge? Potential is what over charge? Energy, right. So field is force per charge, potential is energy per charge. So I'm going to have a charge, and then over here in space, I'm going to describe the potential at a particular point in space. Sort of like the field in that way. I don't have to have another charge over there. I only have a single charge. But if I were to put a charge over there, it would experience the amount of energy that is described by the potential. All right, so it's sort of a construct that we've made up, but it works to help us describe how these charges interact. Now the electric potential is given by this, kq over r. Be careful because we've seen a lot of similar equations. We had F equals kqq over r squared. Unlike the field and potential, you got to have two charges to experience a force. The electric field was kq over r squared, and now our potential is kq over r. We have a reference point, is that when r goes to infinity, when r is really, really big, what happens if r gets really, really big to the potential? It goes to zero. So right, that's a limit, right? Y'all talk about limits, that if I let one variable approach infinity, or if I let one variable approach zero or whatever, my potential will approach another value. So if I let this approach infinity, this approaches zero, or we just say it's equal to zero. In practice, you know, it doesn't have to be that far away, especially if you're talking about little charges. You just move a few feet away, and that's like infinity. That your potential is basically gone down to zero. We can do an ad hoc derivation. We're not going to go through the full derivation, but our ad hoc is just sort of like this, that our delta V is E delta X. All right, remember potential is, or excuse me, I'm sorry, E delta X. We can say that this is equivalent to E times R, so I get KQ over R squared times R, which gives me kq over r. You're not responsible for this derivation, but this is sort of roughly where it comes from. Not responsible for it. All right, y'all ready for this? The electric potential is a it's a scalar quantity. Scalar. Okay. That's a pretty big deal because it makes our math a lot easier. So when we're finding the electric potential due to multiple point charges, kind of like you did on the last test with electric fields, and you'll have to do it on this next test for potential, makes it a lot easier to add up. Because you just add them up like numbers. You just calculate kq over r, and you say, oh, 2 plus 4 is 6, and that's your potential. You don't got to do all that business with the vectors. In fact, we're basically done with vectors. Mostly. We'll have a little bit more. So the potential of multiple charges adds like numbers, not like vectors. We'll see vectors a little bit, but nothing like we've done before. We're basically done with that part. All right, let's look at this. I'll try this. Which of these statements is true at the point P? So I have this point P. It's equidistant from these four charges. And I want to know what is true about the center of this square, about the electric field and the potential. Now let me clarify. The electric potential is a scalar quantity, but the electric potential due to a negative charge has a negative value. Kind of like how work was a scalar quantity, but it could still have a negative value. It had to do with the energy giveth or taketh away. I can have, at this point, an electric potential that is negative due to those negative charges. So what you want to do here is ask yourself, do the potentials all cancel out at point P? That is, am I equidistant from an equal number of positive and negative charges? And then also ask yourself, what is the direction of the electric field at that point P? And is the electric field go to zero at that point? And in that case, you need to imagine that you have a positive test charge here, and then imagine what is the direction of the force that positive test charge feels, and then draw out the vectors, and you'll see whether or not the electric field goes to zero or not. Sometimes it'll cancel and sometimes it won't. All right, we'll stop at 2:05. 2:05. Oh, no class on Monday. Are you serious? We're not having class on Monday. I meant to tell y'all. I'll send you a message to make sure everybody knows. But I have a meeting. I'm part of this whole DOE business. We're doing revising the content standards for K-12, and so we have our last meeting. Woo! But I'm also not giving you. You don't come in. You're not doing a pre-test or any of that jazz. It's not having class on Monday. Okay? Don't tell anybody. They'll dock my pay. All right, I'm going to stop this. All right, let's see. So the potential is definitely zero. The potential is zero because the potential of this charge cancels with the potential of this charge at that point, and the potential of this charge cancels with that charge. I have two positive, two negative charges, so the potential adds up to zero. Now the electric field at this point, due to this charge, is in this direction. Due to this charge is what? It's in this direction. Due to this charge, it's in this direction. And due to this charge, it's in that direction. So the electric field is equal to zero because I have equal but opposite vectors. So the electric field is zero and the potential is zero. See, some of you put C. Okay, yeah, we definitely know that the potential is zero, but the electric field is also zero, so that C is not correct. Let's do a quick example. I'm going to let you go a few minutes early because I have another meeting at 8:30. But so I want to know the potential at point. I know. Now this is a fun meeting. I'm going to middle school, and we're gonna build like a wind generator, a wind turbine. So here, what is the potential at point P for these three charges? You have one in your homework like this, and sometimes you got to do a little trig to get the distances, but V is equal to V1 plus V2 plus V3, and that's all it is. I say V1 is K times Q1, which is, I'm going to go ahead and put in the numbers here actually. 9 times 10 to the 9th, 3 times 10 to the minus 9, divided by 1 meter, KQ over R. And then since they're all the same, I can just multiply this times 3. I can write it out if you want, and that's fine if you want. But I'd have this plus the same term plus the same term. And so that gives us a total potential of, let's see, often on the test the numbers work out easily, so check that. These cancel. 27 times 3, that's 81 volts. What do you think would happen if I said this one's negative and this one's negative? I would subtract them out, right? So I would say, instead of that, I would say it's each one is 27 volts. So I'd say 27 minus 27 minus 27. And so if Q2 and Q3 were negative, my voltage would be negative 27 volts. If they were all negative, it would be negative 81 volts. Okay, so with potential, when you're calculating potential, you have to carry the sign in the calculation of the charge. We didn't have that before because we were dealing with vectors, but now that we're dealing with these scalar quantities, potential and potential energy, which we'll get to next time on Wednesday, you need to carry the signs. So you might want to make a little note to yourself, when I'm calculating potential, include the signs of the charges. There's some homework problems. I recommend in your 20 minutes today that you work through those homework problems. Of course, you've already worked through the chapter 1.5 homework problems. And so tonight, or this afternoon, you'll spend 20 minutes and just pick the first couple of questions from this chapter to work through. Homework's a good place for you to practice for that exam, okay? Y'all have a great weekend. I'll see you Wednesday, and I will send a message out regarding Monday, no class. And I was just joking. You can tell whoever you want. It's not a secret. I tell my department head. He knows I'm not going to be here on Monday.